Hello, everybody. Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history and the present capability and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We have launched the CDM Hub back in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. We envision CDM Hub to become the premier resource for composite design and manufacturing. And CDM Hub provides a very powerful website called cdmhub.org for the global composite community to come together to carry out this mission. You are welcome to join the global composite community currently with more than 12,000 registered users. This webinar series is one of the initiatives CDM Hub started as a service to the global composite community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Solvay, and Anna Swift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will last about 45 minutes, where we will have about 10 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the presentation, the moderator will read your questions for the speaker to answer. Next, let me ask Professor Byron Pepys to introduce our distinguished speaker today.
Welcome, everyone. I'm delighted to introduce to you today Professor T.E. Tay from the National University of Singapore. Dr. Tay he is professor at Mechanical Engineering Department of the National University of Singapore. He obtained his PhD in solid mechanics from the University of Melbourne, Australia. He is associate editor of the Journal of Reinforced Plastics and Composites and serves on the editorial boards of the Journal of Composite Materials, the International Journal of Damage Mechanics, Applied Composite Materials, and Multi-Scale and Multidisciplinary Modeling, Experiment, and Design. He is the author or co-author of 116 international journal papers. He has 3 book chapters, 3 patents. His scholarship has received over 7,000 citations, and his Google Scholar H index is 34, while his I index is 127. Professor Tay is a recipient of the JEC Asian Life Achievement Award. He is a registered professional engineer, founding fellow of the Singapore Academy of Engineering, and council member of the Asian Australian Association of Composite Materials. He was head of the Department of Mechanical Engineering at the National University of Singapore from 2011 to 2015, and vice dean for research from 2009 to 2011. Professor Tay's current research interests are in modeling and progressive damage. You'll hear much about this today. Indeed, he specializes in failure and fracture and impact and computational methods in composite materials to study these problems and issues in multi-scale modeling, natural fiber composites, hybrid composites, molecular mechanics of polymers and composites. And to date, he has graduated 12 PhD students, 20 master's students, and in the university, he teaches senior undergraduate courses in aircraft structures and graduate course in plates and shells. I'm delighted to welcome welcome Professor Tay to this series in which we celebrate the careers of the most outstanding scholars in composite materials in the world. Dr. Tay.
Good morning, or good afternoon, or good evening. It is midnight here in Singapore, so I thought it might be appropriate to show a nighttime photo of the downtown Singapore. And I am very privileged and honored to be giving this talk and to share with you the work that my research team has done in multi-scale and multi-fidelity modeling of progressive damage in composites. I'd like to acknowledge contributions of current team. Professor Vincent Tan is my colleague, Dr. Jie Zhi, and Dr. Kartik, my postdocs, K.H. Leong and K.M. Yu, my PhD students, and also contributions from my past PhD students and postdocs, Dr. Chen Boyang, who is now with TU Delft, and Dr. Lu Xin, who is now with Shanghai University. This is an outline of my talk. In the introduction, I will briefly talk about the modeling techniques, two common modeling techniques that we have encountered today, and also the development of the separable cohesive elements. The smeared crack models is essentially degraded material properties to the model damage, and a discrete crack model is explicitly model the cracks by partitioning finite elements. And then we will present our idea is to combine the smeared crack and discrete crack model into adaptive discrete smeared crack model, which we call ADiSC. And we will talk about why we do that. And then we can actually improve on that model using adaptivity and put in multi-fidelity in the model. And also, I would like to talk about an approach to concurrent modeling, linking the micromechanical to the macromechanical scales. And then we call this the Direct FE2. And this is different from the conventional FE2. Throughout the talk, I will use various examples for verification and of the results and the modeling, using examples in open hole tension, static indentation, and low velocity impact of composites. And finally, I will conclude with the outlook and accept the Q&A. Now, if you look at a typical notch composite specimen, such as an OHT specimen like so, you'll find there are combinations of distinct matrix cracks, diffused, very small but numerous micro cracks, as well as the laminations and possibly fiber damage. Clearly, to capture the physics of these failure modes presents a huge computational and modeling challenge. If you read the early literature, let's say in the 1980s, on notch composites, you will come across criteria such as a point stress or average stress criteria, which are essentially empirical criteria, not really based on much physics. Therefore, for every change in laminate stacking sequence, or let's say an OHT specimen, you will then have to vary the critical stress and so-called characteristic length. So for thousands on thousands of specimens, you may have very different criteria. So clearly, this is not a satisfactory situation. Fortunately, our understanding and modeling of progressive damage has improved considerably since then. Our models have also evolved in sophistication, as we shall see. Most high-fidelity modeling of progressive damage are conducted at a meso or ply level scale, in the picture shown in the middle here. Of course, you have the larger scales in the component and structural scale, the macroscale. And these models are usually modeled using shell or plate elements. At the microscale, you can explicitly model the fibers and the matrix material. However, these are usually of the order of micrometers. We can resort at the mesoscale. We can resort to either discrete or smeared crack methods. Okay, so the discrete crack models cracks explicitly by splitting or partitioning the finite elements, but that comes with a high computational cost. Examples of these includes the XFEM, the Fenton node method, the augmented finite element method, and something which we developed with a group here in collaboration with Professor Pino from Imperial, floating node method. Also, alternate method is the smeared crack method. This is probably older than the discrete crack method. Here, the cracks are modeled with a reduced stiffness in the finite element. So this is more efficient, but suffers from possible mesh dependency and convergence issues. Now, the good news is that much of the physics of failure at the ply level scale can now be modeled fairly accurately with high fidelity models such as these. This is an example where the laminate is subjected to impact and then subjected to compression afterwards. Here, the two specimens are quasi-isotropic in the layout. The only difference between the two on the left and the right are the order of the second sequence. The laminates are first subjected to low velocity impact, and then the damage are retained in the model. Then the boundary conditions are changed such that it is subjected to compression. So depending on the layout sequence, the laminate on the left fails through global buckling, whereas the laminate on the right fails through sublaminate buckling. And these results can be corroborated with experimental data. With the development of the discrete crack technology, we can further improve accuracy and fidelity of modeling. Here, we developed the floating node method to partition not only the brick finite elements, but also the cohesive elements here. The work floating node method is largely due to the work of my ex-PhD student, Dr. Chen Guoyang, who is now a professor at the TU Delft. And the work on the separable cohesive elements are largely due to my ex-student, also Dr. Lu Xin, who is now with Shanghai U. So if you imagine a finite element model, let's say here on the top left corner of a composite laminate, upon damage initiation, the nodes are seeded onto the brick elements to simulate matrix cracks by partitioning the elements. So the elements here, for example, a partition element in this plane. With this will be the matrix crack. So the word is called floating node because the nodes floating before it's seeded and given, if you like, assigned to an element for partitioning. Separable cohesive elements are inserted in between plies for modeling possible delamination. The partitioning of the brick and cohesive elements must be made compatible to enable correct interaction between matrix cracks and delamination. This is particularly important for delamination migration between the interfaces. The floating node method was successfully used to model cracks and damage in both notched and unnotched laminates. So here, the delamination is indicated by the red-colored areas as modeled by cohesive elements, while the matrix cracks are modeled by partitioning the brick elements in the plies. We then extended the discrete crack method to model open fold compression. So this development involves a geometrically nonlinear formulation, and the work is largely due to my postdoc at GGA. It's also my ex-PhD student. Because the open hole compression involves an additional failure mode that is due to sublaminate buckling. So he also applied the code to low velocity impact of composites, shown below here. And here we can see the classic peanut-shaped delamination pattern and matrix cracks for a cross-ply laminate. We've done it also for quasi-isotropic laminate, but it's not shown here. So we now have two technologies with different advantages and disadvantages. The discrete crack model is closer to the physics of fracture, but it's computationally expensive, and therefore it's not so practical for application to larger structures. Smeared crack model, on the other hand, is relatively efficient, especially when numerous micro cracks need to be modeled. But it may have convergence and distortions issues and are generally unable to model interaction with delamination accurately. So in problems where there are delamination migration, these smeared crack models may not work. So the idea here is why not we combine the best of the DCM and SCM models in a single model. The DCM is only used or activated when damage is actively progressing, and where fidelity to physics is important. So it is activated only when it is the damage is growing. But the SCM or the smeared crack model can be used when large number of saturated diffused microcracks are present, or when damage is no longer active and the damaged region can be smeared with reduced stiffness properties. Clearly, there has to be some criteria for some retaining some of the cracks in the discrete form and smearing the others. So we call this method the ADiSC, and it's first proposed in 2019. So the hope here is that it's possibly less compute intensive for larger structures while preserving the fidelity to the physics. And more recently, we've extended this idea to include adaptivity with different element types. This has several advantages. And many practical structures are modeled with shell or plate elements. When failure is predicted to initiate, the surrounding region, let's say, for example, around a notch, may be converted to 3D brick elements, and the discrete crack method may be employed to model the physics of crack growth. When the damage has stopped or reached saturation, a region may be converted back to the more efficient shell elements with lower fidelity. So you have a beginning with a shell model, then you have a transition to 3D where all the damage takes place, and then when the action is over, you convert the region back to shell. It is hoped that this will improve computational efficiency without sacrificing fidelity to physics. Okay, so this work has just recently been published this year. Of course, when it comes to implementation, the devil is in the details, as I say. This includes ensuring the energy consistency in the model transition from a pure DCM model to a coupled DCM SCM model. And then we have to make the decisions when to smear the cracks, when to transit from the DCM to coupled model, when the cracks are saturated. For practical reasons, there must be a assumed minimum crack spacing depending on the mesh size. And then there's also a few larger critical cracks which may still grow, and these may not be smeared, so that the fidelity for these large critical cracks may be preserved. So these parameters have been studied in greater detail in a paper. So I'd like to demonstrate this approach in a OHT of a quasi-isotropic laminate, for which experimental results are well documented by a paper from Steve Hallett. Here, we show the modeling with full 3D discrete crack model. And on the right is the picture of the experimental results from the paper. So here you can see that the elements are partitioned from and the cracks. There's a longitudinal split at the 0 degree ply, like so. In this slide, we show the model with the ADiSC method. Some of the matrix cracks, for example, in the 90 degree ply, has reached saturation and stopped growing, and so have been smeared. So the colors, the region with the colored colors, are the smeared region. So, but however, you can still see that some cracks are still retained as discrete cracks because they continue to grow, and particularly the large longitudinal splits that you see here. Okay, so this is also the smeared regions for the minus 45 internal ply. So this slide shows a summary of the final comparison between the 3D, full 3D discrete model and the ADiSC prediction on the right at various stages of crack growth. This slide shows the predicted load displacement comparison between the, there are various models here, the pure DCM of discrete crack, the pure smeared crack model, and the ADiSC prediction and the experiment here. So it is worth noting that the pure SCM smeared crack model failed to converge, even though we do get the maximum load peak here. So using the ADiSC, it is possible to get maybe about 30% of computational saving. As I've said previously, we can further improve this ADiSC model with adaptivity with different element types, transiting first to from shell to 3D elements, and then back to shell. So in this slide, we show the same open hole tension specimen. However, initially the elements in the white region here, they're all shell elements. And then when damage is predicted to occur around the hole, the shell elements are converted, transited into 3D brick elements denoted by the pink region here. Then damage is, progression is allowed to proceed with the discrete crack modeling. And then when the micro cracks become saturated, the region is then converted back to shell elements with smeared crack properties. And that's denoted for each ply with the colored regions, the different colored regions. So for example, here, the 90-degree ply, the smeared regions are denoted in green, the -45s in blue, and so on and so forth. This is a similar OHT specimen, except that with blocked plies. So there are 4 of each plies here, like this. And this kind of specimen is has a greater tendency to delaminate. So in addition to modeling the matrix cracks, you actually can predict the delamination growth and the various interfaces as shown in the pictures with the red regions here. So there can be further savings of maybe about 20% in computational time. So we have been applying this multi-fidelity model to static indentation. For example, here, this is a problem with static indentation. So the top picture here is a full 3D discrete crack model with the matrix cracks here, and then the delamination prediction. And then the lower one is the multi-fidelity, adaptive multi-fidelity predictions. Oops. Yeah. And the savings in computational time for these models here is a little bit more, about 50%. So these are some of the related publications for the work that I just mentioned. So this is a partial list. If you are interested, I am happy to give you more references on this. Now, I'd like to talk about a technique called the Direct FE2. So far, I've been talking about the modeling progressive failure at the meso and macro scale so far. So I'd like to share a technique called the Direct FE2, which we've been working on lately, that enables us to concurrently bridge the microscale and mesoscale in a single analysis or single model. The Direct FE2 idea is largely credited to my colleague, Professor Vincent Tan, who found a clever way to perform FE2 without having to write very complicated codes. Very briefly, by replacing the homogenized material properties of a macro finite element with RVEs of the fiber matrix composite at the Gauss point, we can perform the multi-scale analysis in a single step, single model. So for example, here, well, we have two adjacent plies. The blue one on top is oriented at an angle plus theta, and the green one at the bottom here is oriented at 0 degrees, let's say. And let's say they are modeled by 3D finite element brick elements. And so for each of these elements, you would have 8 Gauss points. And so for example, the top ply here would have the Gauss points. These are the RVEs, the simple RVEs with the fibers and the matrix at the Gauss points. So the magic sauce of the FE squared, the direct FE squared, is that by scaling the volume of the RVEs, that's found by Vincent, to ensure energy equivalence between the RVEs and the macro elements, we can show that with minimal Python coding, we can use direct FE squared in a commercial FE software such as Abacus. That's a big deal compared with conventional FE squared, because the features such as in a commercial code, such as finite deformation, viscoplasticity, damage models, etc., remains available to the user of the commercial code. So we have done various problems with we have solved various problems with FE squared, direct FE squared, and published them. I will give you a brief reference later on. More intriguingly, for damage progression in composites, this raises a possibility of formulating a failure criteria at the microscale. And because we can now do this analysis in a single model. So this raises a possibility of a micromechanical failure criteria, which could be more fundamental using the constituent material properties such as fiber and matrix. We know that, for example, there are probably a dozen or so of failure criteria at the meso scale, including well-known ones like the Hashim criteria, the Chai-Wu criteria, and so on and so forth, which are semi-empirical in nature, right? So probably if we can do direct FE squared for progressive damage, then there is a possibility of using micromechanics level type of failure criteria instead. So we've actually coded, used the direct FE squared in a shear flexible beam element in Abacus. So this work is largely done by a PhD student, Kirk Ming. And then here we have a macroscale beam element like so. And then there's two Gauss points. And then at the Gauss points, we have a mesoscale RVE. So this RVE will just have fibers coming out of the plane like so. So here we can have the strain energy equivalence. This is the scaling factor that has to be applied to the RVE. So this is the magic sauce that I mentioned just now. So this animation shows that the deformation of the direct FE square model is similar, and the stresses are similar to that of direct numerical solution model, which is basically just a very large finite element model of the whole thing, the whole beam, basically. And then it's possible to show savings in computational time compared to the DNS model as well. Okay, oops. Yeah. Here in this slide, we applied the direct FE2, the model of foam core sandwich beam under bending using layer-wise Timoshenko beam elements. So here we have three beam elements here like so, and then the middle one here is actually represented with foam core. So this is the DNS, a direct numerical solution model. So actually, although this appears like a block of gray rectangle, but it's actually a very, very fine finite element mesh here. And below here, this is the layer-wise beam element. So the each of these strips here represent the RVE, the representative volume element at the Gauss points. So this is what it looks like, the RVE. And the problem is a sandwich beam with steel face plates here and there, and then this is the foam core. So the interesting thing here is that if you look at the deformation of the voids, I don't know why this. Okay. You can see that the deformation of the layer-wise Timoshenko beam and the DNS deformation is similar. Okay, so we have begun to model the damage in open hole tension. This is still a very preliminary work, and using a very coarse macroscale finite element mesh. And then in this case, we use a Mindlin plate. And then we have in each of these plate elements, there are 4 Gauss points in which we place the RVE. So in this case, the RVE is a stack of plies with cohesive elements inserted in between each of these plies, like so. And so the idea here is to see if this FE2 method can predict the lamination failure at the cohesive elements of the RVE at the Gauss points, or at least very close to the whole edge. Okay. The animation has stopped working, but anyway, the animation is supposed to show the cohesive elements with colors here, indicating that possible delamination has occurred in some of the interfaces. So the picture here actually shows only the cohesive elements of the RVEs. So the blocks of plies are not shown here. So I'd just like to briefly talk about the other work that we've done in Direct FE2. So these papers are arranged in chronological order. The first report of Direct FE2 using CFRP beam demonstrated a large deformation in material nonlinearity. So you can see here the deformation of a beam and then the RVEs at the Gauss points. Then this is a review paper outlining the difference between a conventional FE2 and the direct FE2 method. And then this paper also shows that there can be significant savings in computational cost using direct FE2. This is an interesting paper, and it is the first paper that we know of where we actually damaged the RVE with the application of the direct FE2. This is a composite ring, the CFRP ring, with all the fibers coming out of the plane, and then it is subjected to impact loading. And so the composite ring fractures at this point here on the left, and this is the damage that is predicted, the fracturing basically predicted by the model. So this work was done in collaboration with Professor Koyanagi from the Tokyo University of Science. So this one here is a paper on predicting the stress versus strain plots of angle ply composites. And this one here is the application of direct FE2 to model micro inertia in a dynamic problem. So this one is the coding for shear deformable beam elements. Okay, so those are some of the papers that we have published that is relevant to direct FE2. So in conclusion, I have presented several techniques for modeling progressive damage in composites at various length scales, from the micro to the meso and the macroscale. These techniques have varying levels of fidelity, accuracy, but comes with computational costs. However, by coupling some of these techniques and introducing adaptivity here, so it is possible in principle to bridge the length scales in a single model or analysis. A problem in composites is the transferability of results from one scale to another. So, for example, it's difficult to directly use the results obtained from OHT tests to model damage in larger components. Similarly, it's difficult to use the results from micromechanics directly, even to composite coupons. So an integrated simulation model may help to overcome some of these hurdles. Ultimately, the goal is to be able to accurately and efficiently model progressive damage in practical large composite structures using more fundamentally derived material properties at the micromechanics or even at the lower scale levels. This goal probably remains a dream at this point in time. There's hope that advances and efforts at multi-scale and multi-fidelity modeling are inching closer towards it. So it's not quite morning here in Singapore yet, but I will conclude my presentation here, and thank you very much for your attention.
Professor Tay, thank you very much. I'm Jonathan Goodsall. I'll be handling the question and answers. And a note to the audience, please feel free to put questions into the Q&A box at the bottom of your Zoom screen, and I'll read those and ask those here to Professor Tay. Let's begin, Professor Tay, with a couple of questions around the applicability of the model. People indicate very impressed with the work and have asked, one, applicability to other material forms, such as woven composites, and then also applicability, say, to more complex geometries, moving from flat plates to more complex structures. If you can comment on your thoughts and plans there.
Yes, that's a very, very good question. So for woven composites, that adds another level of complexity naturally to the structure. So if you say just the fiber and matrix, the yarns, that's actually at the micro level. Then at the structural level, you have the macro, but then at the woven architecture level, then it will be a meso level. So you can actually, in theory, you can have an FE2 model that actually, has the information of the architecture, the weaving architecture embedded in the Gauss points of a macro element, a structural element. That is in theory doable, but of course, computationally, that is quite substantial. Then the other question has to do with more complicated architecture, or probably less conventional layout. What I have shown is mainly cross-splice and so-called quasi-isotropic. Now, we are also working on two so-called non-conventional layouts. One is the double-double, which you may have heard. The double-double is actually a family of layouts where it's actually the composite is actually consists of units of stacking sequence that's a plus minus psi and then plus minus theta, where the psi and theta are different angles. So this double-double has got advantages in homogenization and ease of manufacturing. So we can apply this kind of modeling, multi-scale modeling, to this family of layout. The other so-called non-conventional layout, in which we have actually published maybe about 4 or 5 or maybe more papers on this, is what we call a bio-inspired helicoidal composite. This comes from a very fascinating animal, which is called a mantis shrimp. A mantis shrimp has a very hard shell in its club. It uses it to break the shell of its prey, such as crabs. And then now if you look at the microstructure of these shells, what you have is that you have a layout that is like a staircase arrangement, but it is complex because it can go one way clockwise and then go another way anti-clockwise. So this kind of bio-inspired layout is very good for impact resistance. And we have, in fact, shown that if we fabricate some of these laminates using carbon fiber epoxy composites, the performance under impact is actually very good. And however, optimize these layouts is not easy by computational method. It's not easy because you have very large numbers of plies, all with slightly different angles. So efficient multi-scale modeling would help in this situation as well. Okay.
There's been a follow-on question that jumped in with, how about nano kind of materials, graphene and other? The thoughts about how you might incorporate that?
Yes. Unfortunately, that is outside my scope. I have dabbled in molecular dynamics or molecular mechanics and we have done some what you call the bead spring modeling of polymer chains. And then there are methods like the quasi-continuum method, which can bridge between, the continuum and the nanoscale. But no, we're not concentrating our efforts right at this point in time on the nanoscale, unfortunately.
Jumping from nano then to more macro, there's been a couple of questions about things like industrial applications, say structural geometries where the structure is not flat, going from flat coupons to curvilinear, more complex geometry structures. Can you comment on the applicability and what has been done to date in correlation and validation there?
Yes, in principle, there's nothing in the multi-scale framework that precludes curved surfaces from being modeled. So, for example, you can model a part of a wing, for example, using a shell, curved shell elements, and then maybe if you're anticipating an impact damage in part of that structure, then you can actually use these adaptive multi-fidelity model, and then you can convert the local part of the curved shells into 3D finite element. Of course, you still have to preserve the curvature as you do the transition. So right now, published work consists mainly of flat specimens. However, there's nothing to preclude curved surfaces. However, I must mention that, although we have made quite a lot of advances in high fidelity modeling, unfortunately, that it's difficult to make industry accept or apply these because most of these models are fairly complicated, complex to use in industry. So maybe by making it more adaptive, then the industry may be more ready to use this if the things like details such as element connectivity, compatibility, and so on and so forth can be automatically built into the model.
Thank you. There's some questions around. I'll summarize them with plans you may have to give others access to the models. I think this has stimulated a lot of interest. Everything from people wanting to play with different failure criteria, playing with aspects of the model, to applying the model, and so on. Do you currently have plans for providing access to the model in some future time, or currently to the research and perhaps the industrial communities?
Well, if you're talking about the FE squared, it's not that hard to actually use it. My colleague Vincent has actually produced a very nice set of slides that actually show you, how to do it step by step. So if you're interested, you can email either me or him, and then we could look at the request. The other parts of the code, we have had collaborators with collaboration with some Japanese professors. Like, for example, we had a recent collaboration with Professor Ryo Higuchi from Tokyo University, who wanted to use our ADiSC and AMF code to model fatigue in composites. Now, fatigue is a very good problem for this, because the fatigue consists of not just very fine and numerous micro cracks, but it also contains things like delamination and so on and so forth. So he has taken our code, and then we've given some technical support to his team, and he has published a paper based on that as well. I think it's either a conference paper or a journal paper. I can't remember now. So it is possible if there is some serious intent for collaboration, we can explore that possibility.
Thank you. Looking at some of that, where do you see this particular field going in the next 5 years? What do you see are both the major developments and also the things that we will be able to do 5 years from now that we can't do today?
Well, I would say that if I think the trend is that we have to model the progressive damage in an efficient way. So I think the main hurdle is the computational cost and complexity of coding. So if we can simplify the coding and then make simplifications to the physics without actually, making it incorrect, then we can have a chance to actually be able to model progressive damage more accurately and more efficiently. This is my hope. So there is still much to be done, but I think if we concentrate on the damage being localized and being able to grow, and then when the damage is already done, there is no more active damage sites, then that part of the structure can be simplified, and then we have a chance to be able to model things more efficiently. But I think we need to have some experimental data to validate and to verify the codes as we come along.
You're touching on another question that I have, which is, in addition to your own development and likely the increase in computational power that will continue to come, what other external developments need to happen in order to push this forward? What other things need to be developed alongside to help this realize its potential?
Okay, I think the drive maybe will have to come from the demand for more lightweightness due to reducing the carbon footprint and so on and so forth. But there are now more than just the application of the composites are now much wider than just in the aerospace. And then there are also application in drones, things like that. So there may be avenues for a more creative use of composites, less conventional layups, not limiting to just a quasi-isotropic layup or the black aluminum philosophy of looking at things. So once you have non-conventional layups, then you need to have good analysis tools to be able to predict the failure. So this is where I think the driver may come from.
Thank you. Professor Tay, again, thank you very much for your presentation, for these answers. We thank the audience, and we remind you all that we'll meet again on December 8th to listen to Professor Stephen Tsai and his talk. Note this is being recorded, and you'll be able to access this webinar and can ask further questions and access answers on cdmhub.org. With that, we thank you all for your attention and look forward to seeing you all in a month. Thank you.
Thank you.